Okay, so we are recording. Again, this is Joe Armstrong and the Power Systems Virtual User Group for August. I hope everybody is doing well. The pandemic continues, virtual meetings and all that continue. We'll see how long this takes, but really am quite anxious to get it all over with. Just want a couple of reminders before we jump in. The presentation materials are out on the Power Systems Bug Wiki. You can find the link to that and in any of the emails that I've sent out, calendar invite, the reminder, anything you've gotten should have that link in it, and I'll put it out here in the chat session as well. One other thing is, as long as I mention the chat system, on the WebEx event there's a Q&A window and a chat window. If you want to ask questions, please put them in the Q&A window. That's the one that we'll be really monitoring. You know, if you just want to chat, fine, put something in the chat window. But if you have, please put it in the Q&A window. I mentioned the presentation materials are on the wiki. When this is all done, I'll put the replay link out on the wiki as well. So with that, let's jump into our topic here. So for August, I don't know why I do this in the summer, but I've got 2 sessions this month. Just because it was just so loaded with things. So Ralph has agreed to do this for us. He does a best practices for Oracle session, and there's just so much material that we split it into 2. They're still going to be pretty full sessions. So, so this is the first one, and covering memory and CPU. So Ralph Schmidt-Dannert is joining us to present. He's 28 years of experience in IT. He's currently working as an executive IT specialist. He's with the IBM Washington Systems Center, Power Technical Team, basically Oracle at IBM. And he spent most of his career focused on very large database environments, designing them, testing, troubleshooting, high availability and near zero data loss disaster recovery, which is important to everybody. So Ralph has helped customers in a lot of different areas: financial, telecommunications, utility, retail, manufacturing, all this, and basically really to choose the appropriate database and the infrastructure that runs them to meet the business requirements. From databases up to 100 terabytes in size, so really big ones as well. So recently, Ralph has been evaluating and implementing technologies to provide database as a service to customers running their databases on IBM Power servers, either on-prem or now we have the IBM Power Virtual Server infrastructure in the cloud. Cool stuff, you can run them there as well. So this is Oracle on AIX, as well as open source databases on either Linux, running on Linux on Power. So Ralph has been really busy in the database area for a long time, lots of experience there. And with that, Ralph, I'll just turn it over to you.
Thank you, Joe, for the introduction. So I appreciate everybody taking the time to listen to these 90 minutes. Luckily, I got a little bit more time this time around than last time. So if you have listened to this a little bit over 2 years back, there have been updates, changes, so I'm trying to continuously refresh the material as it comes along. So if you don't know me or haven't heard this type of presentation from me before, I'm not really just providing you with some, okay, this is the value you set here and that's the value you set there. I'm trying to provide some background information on why specific parameters of deploying an Oracle database on AIX are important, how AIX behaves in comparison, for example, to other environments like Linux or Solaris, and also trying to spread the audience, not only system administrators, but typically also database administrators and storage administrators, because they all talk different vocabulary, different terms, and I'm seeing way too often that they don't talk to each other, and in the context of an Oracle database, that can be pretty disastrous. So in this session today, I will talk about the memory and CPU aspects. It's actually the easier side. Next week will be the more challenging one with I/O, which is one of the critical things going most often wrong with an Oracle database. So Before jumping in there, just a quick refresher. We have a number of power systems available. They can all run AX and Oracle. So you see them here from scale out to scale up. And the new offering of called IBM Power Systems Virtual Servers, which provide you the opportunity to run Oracle database on AX in co-located to the IBM Cloud on IBM Power Servers, SAN infrastructure, the same like what you would be running in your data center. I also provide some additional information like what systems provide capacity on demand. Power 980 has enhanced RAS or reliability capabilities. One thing I really want to call out here is we now have the IBM Power Systems private cloud solution with dynamic capacity. If you know it under Enterprise Pool 2.0, if you're not familiar with it, I strongly suggest to have a close look at what this new offering provides you in capability and flexibility in something like a private cloud environment in your data center. So let's start off with memory. As I mentioned, I'm trying to provide some concepts. So I'm starting here with the physical memory and the physical server. That's pretty straightforward. In a virtualized environment like LPAR, that physical memory would be just a slice of the physical memory you have assigned. Physical memory in an AX environment is carved up into what's called memory pools, and that becomes relevant as we see a little bit later on. The number of pools is dependent on the amount of memory you have assigned to an LPAR, and you can, via the MSAT-3, you can figure out how many memory pools there are in your environment. Then each memory pool is split up into memory pages. So with AX, we have 4 potential memory pages: 4 KB, 64 KB, 16 megabyte, and 16 gigabyte. Small, medium, large, and huge. So notice that huge in AX means something different than in a Linux environment. Then these memory pages are grouped by either used or free. So it's pretty straightforward, nothing special about that one. But where it gets a little more interesting, so how do memory pages traverse from free to used? It's pretty straightforward. If you are starting your program or process, that process will require memory. So it will be allocated free pages from the corresponding page list. So typically that is 4 KB pages for most AX processes. For Oracle, it can also be 64 KB pages. That's the blue graphs. Then you see the pink graphs where actually I've just noticed that they're the wrong way around, but where the least recently used daemon dynamically can free up 4 KB or 64 KB pages if AX runs short of free memory. And as you see below, if you have if you're running out of space and you have data pages, they may end up as page spaces on disk and on demand. You also see that the LRUD is not involved with 16 megabyte pages or 16 gigabyte pages. Now, to make it a little bit more complex, in AX, we have dynamic conversion behind the scenes from 4 KB to 64 KB based on the need of the operating system and applications. So the process you may have seen in something like, for example, TOP or NMON is PSMD. And that is a process, if you see that being very active, that is an indication that you have challenges with where the physical memory on page size it's currently allocated on. So PSMD process automatically moves pages around on the free list. it can also dynamically aggregate used 4KB pages to 64 KB pages. So that's another feature PSMD provides. Then we also have, as I mentioned, 60 megabyte pages. To create 60 megabyte pages is always a manual process by the system admin. It can be done dynamically, so without a system reboot, but you only want to do that if it's a relatively small number of pages. You will also, I will mention later on, there's also the scenario where AirX dynamically breaks up 60 megabyte pages to 64 KB pages if the amount of 64 KB pages is insufficient. And to make it a little bit more challenging, we also have Dynamic System Optimizer, which can aggregate 64 KB pages dynamically to 60 megabyte pages. And you see that here. So to illustrate that this is not really just paper, but it's really happening, here a graph of memory utilization on the system while I did some activities like starting the database, changing SGA size, stopping the database, and so forth. So I'm in the handout with a full presentation list. There is a slide dedicated to describing what each of these specific steps did. The main point I highlight here in the red boxes is where you see that 60 megabyte pages suddenly disappear and are converting to 64 KB pages. And they are not automatically regenerated. This can lead to very significant paging issues down the road, and I will come back to that later on. So to summarize the page discussion, we had the 4 KB pages and the 64 KB pages, which are both pageable. They are the default page sizes for processes. 4 KB pages are the main or the only page size behind JFS2. Start with AX6 and later, 64 KB pages are the kernel page size, and they're actually also utilized by default with Oracle for 11G and later. And as I mentioned here, you can manually configure the Oracle binaries to utilize 64 KB pages as well. 60 megabyte pages, on the other hand, they are pinned, so they can never be paged. If you have 60 megabyte pages sitting configured and there is no application who can use it, and typically that would be only Oracle, then you have basically wasted physical memory and nobody else can use it. So be careful with how many you create and how you manage them. 16 gigabyte pages, so the huge pages, are typically not used, or I haven't seen any customer using 16 gigabyte pages in an Oracle environment. They are challenging to create, so you basically have to power off the system, manually create 16 gigabyte pages, and then manually in the HMC allocate those pages to a specific LPAR. You will need additional 6 gigabyte pages just for management when you utilize it for an Oracle database. So I've tested it, it works, but I have not seen a specific test case, user case using it in Oracle context. So as you're probably not all coming from AIX, you may be coming from Linux or Solaris, I'd like to highlight how overall memory is managed in AIX. And this graphic shows you at the bottom system memory, so it means kernel. It shows you in red the process memory, which is standard processes, but it also includes Oracle program global area and SGA, so shared global area. That's the main pieces the Oracle database cache, for example, is living in. In AX, if there's memory free and you need to do, for example, file caching, because you read a larger file in, that data ends up at JFS2 file cache, and that guy grows and grows up to the limit of max pin percent. So it's not unusual in the X environment to see very little free memory listed. That's as long as you have also a significant amount of memory in the file cache. You can see that via num_perm. This is not a reason for concern because AX will automatically take away pages from the file cache to give it to any process memory requests. So I already mentioned the LRU daemon, so least recently used daemon. You have one per memory pool. You also have parameters, so num_perm, num_client, which you can find, for example, in nmon, and illustrating how much memory or how many pages are currently used for file cache. Max_perm percent, max_client percent define the maximum amount of memory AX will utilize for file caches. Max_client percent is the more important one these days because that's the one which is controlling JFS2 file cache sizes. Max_perm includes also JFS, for example. Configured are those parameters via the VMO system tool. And we have the key parameters here. One is min_perm percent. I can't stop that one. Hang on a second. Okay, sorry about that. It's probably we have multiple phone lines. So I was talking about min_perm percent, which is an important parameter. It's a minimum amount of file cache AX will provide. If your free memory goes, or the file cache size goes below that value, then that results in AX potentially paging out, or not just stealing file cache pages, but also computational pages, which of course could be computational pages from your Oracle database. I will skip the specific formats at the bottom, but the key point is that this LAUD is for a specific given memory pool and for a given page size. So 4 KB and 64 KB pages are the only ones being evaluated by the LRU daemon. The other important parameter to control in AX is how much free memory is AX trying to make available all the time to provide memory to current requests for processes. These are controlled via min_free and max_free. Again, they are per memory pool and per page size. By default, those values are usable in most environments, and you would only change them if your VM-set free column frequently goes to 0, means AX is running out of free pages to satisfy memory request, and that means it synchronously needs to free up pages used by something else, and your process actually has to wait to get more memory. And at the bottom of the slide, I provide information of how you would go about it, calculating an increased value if you observe that you're running out of free memory all the time. From a paging space perspective, AirX is demand paging policy by default. So it will only utilize or allocate paging space if it runs out of free memory, and it has to page out computational pages to paging space. So that may be different than in some of the other operating systems where paging space is pre-allocated. Once pages are written to a paging space, they will stay there and until the process those pages belong to is terminated. So why is that important? An Oracle database is typically running for a long time. So it's not just an hour, but it may be days, weeks, months. So even a very small amount of paging to paging space caused by the Oracle database can lead over time to paging space exhaustion. If AX runs out of paging space, it will start killing processes. Typically, it starts out with the largest memory user. And the largest memory user in AX in the Oracle database environment is typically the Oracle database itself. So you never want to run out of paging space in an AX environment. At the bottom, I provide you a rule of thumb of how I would size the paging space for an Oracle database given the amount of physical memory I have. But just to repeat, this is not an approach to ensure that you have sufficient memory so that there's basically no paging. Again, in Oracle database environment, you do not want to see any paging to paging space, caused by the Oracle database especially. Another concept I've seen customers struggling with and opening up PMRs with IBM support. Oh, I have memory creep, memory loss somewhere. I'm losing memory while my database is up and running. And where's that memory going? So the typical culprit is JFS2 inode and metadata cache. So if your database is utilizing JFS2 file system for the database and not concurrent I/O or direct I/O, or if it does a lot of small file import, export, over time, these caches will grow. If you have more files, you will require more inode entries, more metadata entries. And if, as you see here, those caches cannot be paged, so they're pinned in physical memory, and they can go up to 7% of the physical memory assigned to an LPAR. So it can be a pretty significant chunk of memory which is mostly wasted, because in an Oracle database environment, the number of files you have is typically pretty small. And my suggestion would be, especially in environments where you have hundreds of gigabytes of physical memory, to carefully evaluate how many inodes and you actually have, so how many files, and then adjust down the J2 inode cache size and J2 metadata cache size to more corresponding values, so you're not ending up with these huge caches. Because they will not be, they never shrink. They only grow until a file is actually deleted. So I already mentioned before that there is a feature called Dynamic System Optimizer. With AX 7.2, it's actually included in AX, but it is disabled by default. I show you at the bottom on how to activate it. So what does it do? It creates dynamically under the cover, out of 64 KB pages, 60 megabyte pages. And this is very beneficial in memory management within AX, because you have a significantly fewer number of pages to manage. And I actually did a small test, and I show you here an example for a relatively small database on how it looks like. So in the bottom right, you can see that I start up the database, that the memory usage increased, in this case 64 KB pages, and this is actually with the most aggressive setting for Dynamic System Optimizer. You can see that around 137, AX started to convert 64 KB pages to 60 megabyte pages, and it took 12 minutes to convert 90 pages to 1960 megabyte pages. On here on the top left, you can see the increased CPU usage caused by that conversion. So it's not that high, but just to be aware of that cost, that there is some cost involved. And at the bottom left, I show you the only way to determine if you have any of those dynamically generated 60 megabyte pages. And you see this is red highlighted. L represents 60 megabyte pages. Important to remember is that when you shut down the database, all those 60 megabyte pages will disappear again. And when you bring it up again, after a while, AX will again start to create 60 megabyte pages out of 64K pages. So these are not static pages, they are transient while a long-running database process is running, and it only applies to the Oracle database SGA. This is an updated slide, so in case you haven't seen it before, I just want to highlight that it's significantly changed. Active memory expansion is actually a memory compression feature which allows to compress less frequently used pages in memory to make up more physical memory for other memory requests. So it's not paging, but memory compression. It's by default, it only uses 4 KB memory pages, and just to make sure, this is a licensed feature you have to buy for your physical server. So it's a server-wide feature code. In the context of an Oracle 12.2 database, it is supported if you utilize 64 KB pages for RAC or for non-RAC environments on Power 8 and Power 9, but it requires current AIX release levels and firmware. You can validate if active memory expansion is available by looking at the VMO output and grep for the AME_hardware_Excel. If that value is 0, that means hardware acceleration is not available. In that case, you cannot use active memory expansion. For Oracle 12.2, as mentioned, you need to use 64 KB pages with AME, and that is set via the VMM_MP size_support parameter of VMO, and you set it to either 2 or 3. If you use AME, you can of course not utilize 60 megabyte or 60 gigabyte pages. In the context of a production database, if you really think that it's beneficial, you need to do very significant testing, because compressing, uncompressing memory pages is compute intensive, even with an accelerator, and has an impact on performance. So this is a feature I would suggest can be very beneficial in some production environments, small dev tests where you want to have better usage of your physical memory. But for actual production environments, I would be very careful or hesitant to utilize that feature. As I mentioned, we have pretty large servers, scale-up servers. So in this case here, it's a dual CAC or dual system node configuration as an example. I picked an 870 here. And I want to talk about the context of local, near, and far memory. And that's important because the shorter the latency or the lower the latency of a memory access is, the faster your database can run, the better your response times will be, the better your batch throughput will be. So it's important that you can try to keep your processor and memory close together. So in this example, you see that 1/8 of the memory is local. The memory is directly attached to the physical core. 3/8 is near. The memory is connected to the chip, but not to the same core. And half of the memory is far, means it has to travel through the connection between the system doors. With Power 7 servers, that was a significant, or could be a quite significant performance impact. With Power 8 and Power 9, IBM has significantly improved on those latencies with far memory access. But from a tuning perspective, you still want to try to make data as locally available as possible. So how do you check it out? What does your current system look like? That's where the command lss-rat-va comes in. Here an example where we have a system with 3 CAC nodes. We have chips in there, and you see that these chips have memory attached. And you see also that how these logical CPUs are distributed over these different domains. If you look closely at the bottom 3 CPUs, they have, or as I said, they have logical processors assigned to them, so they will execute in those SRAMs, but they have no local memory access. So anything which is running on those 3 highlighted at the bottom, logical CPUs, or virtual processors in this case, you can say, will require a far memory access. So the memory will all be on, will encounter pretty significant latencies. If you have this kind of environment, that's in this case it would be 880 or 980, you can utilize the dynamic platform optimizer via the HMC to dynamically optimize that mapping. But beware that this optimization is CPU intensive, and it has a performance impact on the LPAR you're optimizing. So you only want to do that during low usage time periods. So in summary, to get the most out of your system for a given workload, you want to ensure that you configure your LPARs that they can live within the smallest number of CAC. So if your LPAR only needs the capacity of 4 virtual processors, you do not want to tell the hypervisor, oh, let that LPAR be able to use 24. And it's not just the LPARs you activate, but also the maximum size of the LPAR, which tells the hypervisor on how to lay out a specific LPAR over the physical resources in the servers. For shared processor LPARs, don't over-allocate the number of virtual CPUs as compared to entitlement. I'm coming back to that later on, but typically the number of virtual processors should not be more than maybe 2 to 3 of the entitled capacity. Best practices would be maybe 1.5x. If you go overboard there, you can end up with significant wasted CPU cycles, resources, by just switching between too many virtual processors. So that's not something you want to do. The same applies for memory. If your LPAR doesn't need 2 terabyte of memory, just 500 gigabyte, you want to set it in the LPAR definition accordingly. If you say, okay, LPAR, you get 500 gigabyte, but you can go up to 2 terabyte in the LPAR definition of the HMC, the hypervisor will likely spread that LPAR out much wider than you would expect, which again leads to latency and performance impact. And a final best practice, keep your firmware and operating system updated. IBM is continuously improving features in the hypervisor, things like processor folding, and you want to really benefit from those improvements. Now it's a nice message here is, in the context AX, most of the tuning parameters are set out of the box in a way that you can run an Oracle database with no changes required. It's very different than, for example, if you come from a Linux environment. Start with AX61, most of those parameters are actually now restricted. And restricted means you typically do not want to change those parameters without validating or verifying with IBM support what those parameters are. In the extended handout, there is actually a slide where I list all the parameters which in the past we had to adjust, but with current AX releases are already set optimally by default. Wrapping up this section here, I just want to make you aware of that there was an issue recorded, so you may want to look into this LPAR. I provide a link up there, and it can lead to increased memory consumption. And there is an eFix available, and there's also the workaround I provide here. So just for your awareness, that's pretty new, so added it here. So where does Oracle really use memory? The biggest chunk is the system global area, the shared pool, database buffer cache. If you're using the Oracle in-memory feature, the in-memory area, buffer redo logs. Those are the key areas. They are all shared between all processes, and it's typically the biggest chunk. Then we have program global area that's private to the Oracle server processes, and you see they are highlighted here in blue. And I also highlight some of the key Oracle processes like LogWriter, PMON, SMON, user processes, DB writer, involved in an Oracle database instance. But the blue highlighted is really where Oracle is using memory. So of course, for computational, it's the Oracle binaries, but it also includes Oracle SGA and PGA. File system cache, if you're using the JFS2 file system, then all your database files, video log files, archive logs are utilizing the AX file system cache, except if you specified direct I/O or concurrent I/O. And I spent quite a bit of direct I/O, concurrent I/O next week. From a virtual memory management perspective, just to repeat, you do not want to overcommit memory. So you want to look, okay, my SGA, my PGA in an Oracle database, how big can they grow? And I want to still have about 10 to 20% of physical memory unallocated for those areas, because there is, depending on how many database connections you have, there can be quite a bit of variability over time how Oracle processes memory requirements are. So from a little bit switching to the database administrator view, so that the system admins between you have heard those terms. All those features, I start with 10G, but they are also available in 12C, or it's now 18 and 19. The first one was introduced with 10G, called Automatic Shared Memory Management. And that management feature controlled key memory constructs within the database, like the database cache, shared pool size, large pool size, and so forth. The maximum is specified via SGA max size, and remember that name because it has a role later on. SGA target, that is what you tell the database, okay, this is the initial goal I want to have as the memory allocated to those different areas. With 11G, we also introduce automatic memory management, and that parameter does not only control the shared memory area, but it also controls the process global area. So SGA and PGA are both capped. By the way, they are not hard capped, but Oracle tries to adhere to it via the memory target and, of course, memory max target. By default, if SGA target and PGA aggregate target are not set in the database, the database gives 60% of the memory target to the SGA and 40% to the PGA. Relevant is this memory management feature, especially if you have very varying workloads, where you have a time period during the day where you heavily, for example, rely on buffer cache hits, and you need more space in the SGA, and then you have a switch in workload characteristic where you need more memory in the PGA, for example, for large sorts. And Oracle Automatic Management dynamically adjusts the memory sizes based on observed usage. From my experience, Oracle can be a little bit overactive, overreactive to even small changes in requirements. And in the highlight box at the bottom, I provide you a meta-link note where you can influence how often Oracle executes these memory adjustments, because they basically force the database to stop, adjust the memory allocation, and then continue. So it can be somewhat disruptive, and it can take seconds, which may be more than you would expect. With Oracle 12c, Oracle went a little bit further. Now you can specify a P-grade PGA aggregate limit. And this is close to a hard limit. It is not a really full hard limit, but it's much closer to it. Where Oracle checks for all its processes how much PGA memory space they have used. And if the sum is larger than the PGA aggregate limit, Oracle will start killing processes, typically starting with the one having the highest amount of PGA memory allocated. Another new feature with Oracle 12c is Oracle in memory. Basically, data stored in memory, not in the buffer cache, but in specific format, hypercomma compressed. And you need to specify a specific size allocated out of the SGA, and that is the in-memory size. So it can be specifically defined, and with 12.2, you can dynamically increase that size allocated from the SGA, but you cannot decrease it. From my experience, I typically suggest to customers to use SGA target and SGA max size rather than memory target, memory max target, so I don't get the automatic memory rearrangements, which can be quite disrupted. But some workloads may need the memory settings. One thing I noticed from a customer is that memory target, memory max target are not hard limits. And with 12c, we actually have seen that we specified, or the customer specified, the memory max target as 210 gigabytes. And in reality, if you looked at the Oracle performance report, so the AWR, that Oracle utilized 103% of physical memory. And you can imagine what that means, right? It's paging to paging space. So be careful that those parameters are not hard limits, and you want to monitor your AX environment on a regular basis on how much memory your client processes typically utilize to ensure that you're not running out of memory. Another change you may or may not be aware of is, it was not really that well announced. So if you're coming from 11G, for example, with Oracle 12.1, pre-page SGA is suddenly set to true. It was before the default was false. With true, that means now every time an Oracle process starts or you connect to your Oracle database, the first thing it does, it touches every memory page in the SGA. The pro is, after that initial touching of all the memory pages to basically map them into the memory, the address space of the process, it has not to be done again. The challenge is, it can take quite a time to touch all the memory pages, depending on your page size. So in the table below, you see some examples. If you have a 250 gigabyte SGA size, and you're running with 64 KB pages, each process has to page 4 million pages or touch them. And if you have 10, 20, 30 processes trying to do that in parallel because you have a connection storm, that puts significant strain on AX virtual memory management and can lead to significant delays in connection startups. So our suggestion here is to set it back to the previous value of false, especially if you have larger SGA sizes. Now to one of my, let's say, a little bit favorite topics is log SGA equals false or true. So what does log SGA mean? That is, as the name implies, the DBA can set this parameter for the database. When the database starts up with log SGA equals false, Oracle dynamically allocates pages for the SGA only on demand. So it starts off with a relatively small amount of memory, and the database is very quickly available. If more buffer cache is needed or more PGA memory, Oracle dynamically allocates more physical memory pages at that point in time. So you will see memory usage for the database going up. SGA target, as I mentioned, can be dynamically adjusted. So if you find that you have SGA max at, let's say, 200 gigabyte, you start with SGA target at 100, you can dynamically increase that to 120, 130 to be able to adjust, for example, your buffer cache size because your workload has changed. 64 KB pages are typically used in this configuration. There's nothing you need to do about it. If you start your database with a significant large SGA and you had 60 megabyte pages in your environment, AirX may decide to down convert 16 megabyte pages to 64 KB pages for you to be able to bring up the database. So be aware of that. There is also the option here at the bottom where you can specify other page sizes, Oracle SGA page size. And if you utilize that option, Oracle will allocate pages as specified by the SGA max size, even if log SGA is set to false. So be aware of that. Log SGA equals true. This means that Oracle at startup will pre-allocate all memory physically as specified by SJ max size. So if you set SJ target to 100 gigabyte, you set SJ max size to 200 gigabyte, Oracle will allocate at startup 200 gigabyte. You can imagine that that can take some time. If you are going with really large database like a terabyte of SJ or 2 terabytes, that can be half an hour to an hour if you use 64 KB pages. So be aware of that. So I just recently did a test with 3 terabyte, and I waited for about an hour for the database to start. I switched, and that is one of the reasons why I bring it up here. I switched to use of 60 megabyte pages, and the database came up in 20 seconds. So that shows or illustrates the benefit of 60 megabyte pages over 64 KB pages, especially for large SGAs. This is a little bit of modified suggestion from previous sessions. So if you have large SGA and you have strong memory monitoring controls and your system admin and DBA talk with each other, then I would suggest to pre-allocate 60 megabyte pages and utilize 60 megabyte pages for the SGA of the database. If you do not have strong controls, then I would still advise against it. Because if the DBA does a fat finger and accidentally makes 100 out of 100 gigabyte, 1,000 gigabyte, he can bring down AX by paging to paging space. So that is the risk of using log SGA and 60 megabyte pages if not adequately configured. And here's just a page on how to activate it. So it's not just log SGA equals true from the DBA side. You also need to configure how many 6 memory pages you want to have, and that they need to be pinned. And you need to give the Oracle user some additional capabilities that he's allowed to allocate 60 megabyte pages and pin them. Thanks to Nigel, I think he was also on the phone. Nmon has a I find Nmon here to be a very handy tool to figure out, okay, how many 60 megabyte pages do I have? And are they actually used? And so if you do Nmon with 1 capital M, you get it in pages. If you add another M, you get it in megabytes. So if you are running your database and you think you're using 60 megabyte pages, I suggest to have a quick look at Nmon and see if the number of memory frames allocated and the number of free list pages reflect that the database is actually using 60 megabyte pages. If not, you are probably in for some trouble down the road, as your DBA has incorrectly specified the SGA size, and AX decided to switch to 64 KB usage instead. To finish up this memory section, I thought I'd bring up again the Oracle in-memory option, which allows to store tables in columnar format compressed in memory. It is a pretty pricey option, but I suggest you spend a little bit of time looking, okay, what can it provide as benefits, especially in a data warehouse / OLAP kind of workload environment. So if you see on the bottom right, that's standard row format, so no in-memory option. With 36 cores, we went to 72 cores. We got about a 44% improvement in throughput as measured of how many queries could actually get completed. I then activated in memory. So the key data tables were in memory compressed in columnar format. And with 8 cores, instead of 72, I got 3x the throughput. And it also scales very well. So with 16 to 36, I got about 2x the performance. So you can utilize the in-memory feature to save on CPU and, of course, also I/O requirements. What is in memory, there is no physical I/O to disk. So this is a feature which allows you to potentially much better support OLTP and data warehouse queries within the same database. So I draw a quick stop here. So any specific unanswered questions in the Q&A? Joe is on mute, or I'm not sure.
Yeah, sorry, Ralph. Thank you. Yeah, there's a few questions, Ralph. Let me just take a couple here for you. One is there a minimum SGA size after which we should consider using 16 megabyte pages?
I would probably start looking into it at about 150 gigabytes.
Okay.
And if you go into terabytes, for sure.
Okay, so here's another question. I don't know if this is going to be beyond the scope or take up too much time, but here's the question is, can you please throw more light on computational and file memory? Why does AIX take almost all the available memory on the server?
So the idea, it's relatively simple to answer. The idea is that we have the physical memory, we want to use it. Unused physical memory doesn't really provide any benefit. And that is a philosophy AIX uses or has used forever. And you can control, if you prefer to see a higher free memory in AIX, you could, for example, artificially reduce the maximum size, the max client percent of your AIX JFS2 file cache if you want to. But it's a philosophy, and I think I agree with that approach, because if the memory is there and I can use it, for example, to cache data I believe I will use later on again, why not use it?
Okay. I'm trying to pick out some a little bit faster ones. What are the only 2-page sizes that LRUD examines?
4 KB and 64 KB.
All right. In the installation guide for Oracle database tells us that the minimum and maximum perm for FSC are 3 and 90%. This, in your experience, this okay depends on ASM or FS system?
I did not get that.
Yeah, it's worded a little bit weird. I'm not sure.
Let's skip it, and maybe you, whoever asked it, can revert a little bit, and we can get back to it at the end.
Okay. Yep. To help avoid SRAD fragmentation, should I set my LPAR min memory equal to desired memory? Otherwise, min is initially allocated, then it went away from me.
No, the desired is the initial. Sorry, desired. So desired is what the hypervisor tries to allocate to the LPAR.
Right.
Min is the smallest value you can dynamically reduce the LPAR memory size to. So that the min and desired is not that important. What is important? So the desired is important, so you don't want to over allocate. The max, but the max is important as well, because the hypervisor looks at the max and tries to determine, okay, if the LPAR dynamically would grow sometime in the future, what would be the best resource allocation in that case, and takes that into account when it determines how to allocate CPU and memory to an LPAR.
Okay.
And the same applies to CPU.
And for everybody, two things. One, the LPAR, the EFIX that Ralph mentioned, the slide went by if you missed it. The presentation materials are out on the wiki. You can go download those and get all the links and stuff from there. And two, Ralph mentioned briefly in there an extended version of the presentation, which he sent me, but he asked not to put on the wiki until after the session was over. So after the session, I'll be putting up a little bit of extended version. Ralph, maybe just mention what's in the extended version for everyone.
Yeah, so there are some additional supportive slides. There are some extended content I don't have the time to cover. So my suggestion would be just download it and look it over. The key material, which is current, I'm seeing most customers concerned with, is what I present. Some of these other things in the deck are a little bit more esoteric.
Okay. So I think in the interest of time, Ralph, I'd like you to get on with the CPU so that we can get through that.
Okay.
Why don't you go in there, and then, if we have more time for questions, we'll get to them. What we don't, then I'll send you the question log, and maybe we can do them after the session and post it.
Okay, sounds good.
Okay, good. Thanks.
Okay, thanks, Joe. So I hope everybody is already on Power9. If not, this is a little bit of a teaser of how Power9 differs from Power8. You get significantly more benefit from SMT as compared to Power8. So on the bottom graph, this is actually an Oracle workload where I started out with SMT8 and fully loaded the system. So everything was basically the best throughput I could get. And then I reduced from SMT8 to SMT4 to 2 to 1 and illustrate how the transaction rates went down and how the response time went up with the lower SMT levels. The one thing I really want to point out here is you see a significant jump from SMT1 to SMT2. So with Power9, you basically really do not want to run SMT1. You are leaving a lot of performance unused. And it's really based on how Power9 processor is architected as compared to Power8. And the same will hold true for the Power10 processor, which was discussed on the hot chip, I think, a few days ago. So Power9, typically we would run with SMT8, which is the default now with the latest X releases. Whereas with Power8, SMT4 in some cases provided better performance than SMT8. Don't want to spend too much time on licensing. So licensing and shared processor pools, all these topics are an hour session by themselves. So I only want to highlight is that with Power, in the Power environment, you can utilize capped partitions, so capped LPARs, as an Oracle-accepted hard partitioning technology. You can utilize shared processor pools, which are also capped, to group Oracle workloads or Oracle LPARs in that shared pool. Those LPARs could be uncapped, and they would be limited by the hard cap on the shared processor pool. So in this example here, if you look at the two LPARs and 5 and 6, they're both uncapped. I have a shared processor pool with 5 processors. And for this configuration, even if they are uncapped, so and 5 and 6 are uncapped, I have 5 plus 3, so 8 virtual processors in those LPARs combined. I only pay for 5 licenses because the maximum the Oracle databases can ever use in that pool is the equivalent of 5 processor cores. Also want to highlight, you can, of course, activate via capacity on demand just 1 core at a time, and that would be the smallest license increment. We have very recently renamed, rebranded, extended the Enterprise Pool 2.0 option. I want to highlight that Enterprise Pool does not really have any impact on Oracle licensing, with one exception. If you are utilizing Enterprise Pools 2.0, I use this short name here, then all resources, means all CPU and all memory on all servers in that pool are active by default. So the shared processor pool 0 will have all processors being active. If you want to limit Oracle licensing, you need to either utilize kept CPU LPARs, or you need to specify a shared processor pool 1 or 2, so different from shared processor pool 0 with all the resources, to be able to limit licensing costs. But otherwise, Enterprise Pool 2.0 has no implications on how Oracle licenses are calculated, or it's also not an option to save Oracle licenses. There's no dynamic move of Oracle resources or Oracle licenses from one physical server to another. So to put it pretty frank. In an Oracle database, it's of course aware of CPUs. How many do I have? For the optimizer, Oracle does not look really at virtual processors. It only looks at logical CPUs. Logical CPUs, you could calculate out number of virtual processors in the LPAR times your SMT mode, 1, 2, 4, or 8. So in the database, you have a parameter called CPU count, and that reflects the logical CPUs Oracle has discovered at startup, and it's dynamically adjusted if you do the LPAR operations. Two parameters are especially impacted besides CPU count if you do the LPAR. One is DB writer processes, so it's 1 for every 8 logical CPUs, and especially in large environments, that may be too many. So you may want to then manually adjust the number of DB writer processes down, because having more and more adds just contention, but not necessarily throughput of writing dirty pages back to disk. In a rack environment, GCS server processes can be impacted, and I'm not sure if you're aware, but in a rack cluster, you need to make sure that GCS server processes match for all Oracle instances. Otherwise, rack gets very unhappy. From an optimizer perspective, the number of CPUs impacts parallel queries, and so if you change the number of logical CPUs, you may suddenly see changes in how Oracle decides to execute queries, and that can be beneficial or can be pretty detrimental. It's really it's an independent, unluckily. So some additional parameters, somewhat more recent, which in an AIX, Oracle AIX environment, we typically do not really play with. One is instance caging, which you utilize if you have multiple Oracle database instances from different databases in the same AIX operating system image. And you want to control how much CPU each of those databases can utilize. So instance caging, and together with the Oracle Resource Manager, allows you to control how physical CPU resources are made available to those database instances. Then we have the option to do non-uniform memory access optimization. In the context of Oracle AIX, we typically do not activate that. I personally have not seen a benefit. I think in some of the other environments like Linux, it has more of an impact. With 12c and later, the Oracle database could also be executed in a threaded model. like you would run it on Windows. Default for Aegis on X is process-based execution, and we still suggest to leave it as the default historic value. We have tested a little bit, but we didn't see any benefit. So my suggestion would be it's still pretty new, not heavily used feature for Org on X, and therefore, at minimum, you would do heavy testing. At the bottom, I just FYI that exists, but this is really expert tuning, and I would be very, very careful, and you need to know what you do if you start, quote, playing around with that parameter and RSets. On a high level, this is, hopefully everybody should know that already, but just to repeat, so if you have an LPAR and it's capped, then you want to configure the virtual CPUs for that LPAR to be the nearest integer greater or equal to that capping limit or entitlement. So don't configure more vCPUs than that rule. If you have an uncapped LPAR, so an LPAR which can grow, is more dynamic, can go above its entitlement, a guaranteed resource allocation, for example, to handle peaks. You do not want to go overboard with the number of virtual processors you want to specify. The rule of thumb is maybe 1.5 to 2x the entitlement. If you specify too many virtual processors, you will encounter potential increased latencies in process scheduling to virtual processors, and of course lost CPU cycles with the hypervisor having to dispatch a virtual CPU to a physical CPU when it's not actually has the workload. One thing I'm not actually showing here, the number of virtual processors in LPAR is also a hard cap. So it's not just the entitlement, but the number of virtual processors in an uncapped LPAR also limits how many CPU resources an LPAR can utilize. And a small bug here at the bottom, if you're running 12.1 and with LPARs, you could run into that problem. For Power 9, I already mentioned, I would suggest to start with SMT8, which is now the operating system default for performance testing. I mentioned already DB writer processes. In the context of parallel query execution, you may want to change the parallel threads per CPU to a value of 1. We are already running with 8 SMT threads per physical processor. So doubling the number of threads or processes the Oracle database starts for parallel query, above that value would basically mean I would have 60 processes per Power 9 core. Overloading that core and may actually result in reduced throughput or latencies, increased latencies. Dedicated versus shared CPUs, I've seen that discussion every now and then. I'm not seeing significant performance differences between dedicated and shared, as long as the entitlement for the shared CPU is correctly set. If you want to really get the absolute lowest latency, potentially a little bit better performance, then you could go with dedicated CPU, but you lose a lot of the sharing consolidation functionality which differentiates a power environment from other environments. At the bottom, I mentioned if you go dedicated CPU LPARs, you could still do donating, which would allow unused CPU cycles from that LPAR to still be utilized by other LPARs, but it's significantly less fine-grained than utilizing a shared CPU LPAR. Processor folding, that is one of the challenges I've seen in many workloads with Oracle. I've seen things like you do database import and it gets slower and slower and slower, and you end up with a single process being active. So that's a while back, but if you see something like that, processor folding could be the cause. So what is processor folding? AirX dynamically evaluates every second how much CPU resource is actually used, how many virtual processors are needed to support that physical CPU resource usage, and if there's a difference, it will decide, okay, I'm folding virtual processors and I will not schedule any work to them. If the work picks back up after the second, AX discovers, oh, I need more, it will start unfolding virtual processors automatically. So that is how it works. The goal is really to minimize CPU cycles for managing of unused or inefficient virtual processors. That is the goal of this folding. In the context of an Oracle database, I typically suggest to tell AX keep one or two more virtual processors unfolded than you calculated, and that typically resolves the issues I've seen caused by CPU folding. So, and it's the parameter used is a VM_X3 CPUs. It's a shadow, it's an AX shadow tool. And by the way, if you're running Oracle Rec, that is a requirement. You need to set that value to 2. Otherwise, in low-used Oracle Rec environments, you could end up with no evictions. I've seen it at a customer. So, very important in Rec environment, set VM_X3 CPUs equals to 2, telling AX at minimum keep 2 virtual processors more active than you calculated as physical CPU resource utilization. So one important tool, if you're using shared CPU LPARs, so several LPARs on the same physical server, you want to figure out, is my entitlement good? How much I'm fighting for physical CPU usage with other LPARs in the system. Starting with 7.1.3 SB2 or later, you can utilize the mpset-v command, and it tells you under the VTB column how long a specific virtual processor was actually scheduled and running on a physical processor. So in this case, you see the 4995 milliseconds, and I captured every 5 seconds. So basically, nearly 100% of that 5 seconds, that virtual processor was executing on a physical. If you see significantly lower numbers there, that could be the indication that your LPARs are heavily fighting for physical CPU resources, and you may start to more closer investigate, is your entitlement correctly set based on your priorities? Do you have correctly set the number of virtual processors based on the workload you're trying to achieve? So this is a very handy, quite recent command to get a good indication how efficient virtual processor to physical processor utilization is. 2 more CPU folding issues. The top one is an early one for with Power 9. So you provide the APAR there. So you want to look into that if you have that APAR installed. And the one at the bottom is actually quite new, or the fix for it is quite new. So look at it. One thing, if you think that you have an issue with CPU folding impacting your workload, do a dynamic quick change by disabling it. And I show you at the bottom with the shadow-o VPM_XC CPUs equals -1. You can dynamically disable it and see if that changes your workload behavior. If you see a sudden increase in activity, higher throughput, for example, that is an indication that CPU folding impacted your workload. And if that value was set to 0 before, I suggest to set it to 2 and see if that resolves the issue. And of course, look at these LPARs available here. Switching a little bit more to Power 9, so maximum performance mode, which is the default in Power 9 systems. It's a little bit a strange graphic. I didn't create it, but the green line represents the frequency, so the CPU cycle frequency overload. On the left, you see it at 100% busy, and to the right, you see it up to 0% busy. So you see the frequency at about 40% busy is the maximum, and if you go higher, it goes down. So I decided to do a little bit of real-life testing. So this is a workload which I ran with different SMT levels just to illustrate different behavior. But you can see how flexible and fine-grained this maximum performance mode adjusts frequencies based on workload. And with SMT2, I had the highest workload, here the peak in the middle, but I also had the shortest runtime. And you can see I was running with 3.6 gigahertz, and it dropped down to about 3.4 gigahertz under very heavy load. So PM cycles command allows you to see current frequency in the system, and if you're interested to look at that. But be aware, if you're running maximum performance, you go to very high utilization. Depending on your environment conditions, frequencies and performance can be reduced.
So Ralph, let me just say something to this. The default for Power 9 and the default for is max performance mode. So the default, your systems will come, they'll be running in max performance mode, which means that they'll run at the maximum frequency they can, which may change depending on the workload, because the power draw is really the big thing, not so much temperature, but the power draw is with the voltage regulator is the limiting factor there. But they'll run at the max performance mode they can all the time.
Correct.
At the highest frequency they can all the time.
All right, so there are other options. So static nominal mode, power saver mode, you can configure via the ASMI interface. Right. But default, as Joe pointed out, is maximum performance mode with Power 9. That was different with Power 8. With Power 9, that is the default mode you run in. So my last slide, this is a little bit of an eye strain, but if you are running Oracle databases on AIX with SMT, you probably wonder, okay, my reported CPU utilization in Oracle for Oracle processes does not match what I'm seeing with operating system tools like VMstat or Nmon. So this is what I'm trying to illustrate here. So I have, on the bottom left, I'm showing you the runnable processes, so to run Q and AIX, what is running or runnable. Above it, I show at what point in times I dynamically change the SMT mode. So from 8 to 2 to 1 and then back to 8. And note how long it took to go back from SMT1 to SMT8. So I actually didn't wait for it to complete. That is why the Oracle database was up and running dynamically. On the bottom right, I show the workload. So the orange represents the Oracle CPU utilization. And you see in the blue where I artificially added additional workload. It's basically a dump while loop in a shell, eating up all the resources of a single logical processor. Now, the interesting really is if you look at the top right, what your Oracle Enterprise Manager or what the AWR will tell you. So instance, foreground, and background, that is what the Oracle database thinks it is using as the CPU cycles in the system. All right, so this green area down here. If you look down here, there's nothing else running on the system than really Oracle. So it's clearly misrepresenting or misreporting how much CPU it is using compared to overall. If I go to this is the cron shell, you see it goes up as expected, right? So that is correctly reported. So where it's now getting interesting is I switched to SMT2. The database workload did not change. It's the same workload consistently through, but because I'm switching to SMT2, I'm using more of the CPU resources as reported by X. So X also adjusts CPU reporting based on SMT level. So that's why you see a higher SMT CPU usage for Oracle when I switch to SMT2. And you also see that Oracle is adjusting instance foreground background CPU reported. If you go to SMT2, SMT1, this is what we actually would expect to see in all cases. Right? I'm only running Oracle workload, nothing else. So all my reported CPU cycles, instance foreground background, should match the CPU utilization report in AX. Also note that it seems to be only about, I think, every minute to be updating. And then I switch back to SMT8, and you can see that it goes back down. So it's something to really be aware of. And I'm talking with enablement teams, or enablement from IBM and Oracle to see how this can be corrected. Because it's definitely very, at minimum, misleading if you want to understand how many resources your database is using and you're only looking at AWRs, because they are definitely not correctly reporting. So you need to look at VMstat or nmon in parallel to really understand what process or process type is utilizing CPU resources. And for example, the graph on the bottom right is created from nmon data, from the nmon top data. And with that, I'm out of time. So here, the advertisement for next week, where we go into the more challenging I/O arena, AX with Oracle databases, and Joe. So, any more questions?
Well, there are some questions out there, Ralph. Like you said, we're kind of out of time, but let's see. Here's a question. Can you talk a little about, you talked about the SMT settings, but can you talk how that, like to understand how the SMT settings works with multiple databases on the same host? And if you've tested that.
Yeah, so it's basically independent, right? So SMT in an app. So I assume we are talking about a single LPAR, where we are running multiple databases instances within the same LPAR.
Yeah.
So SMT controls. So SMT controls how many logical processors I have in that LPAR. If I run multiple database instances without any controls in that same AX image, they will basically play as equals, and they will request CPU resources as they need, and AX will distribute CPU resources kind of equally over all the processes running on behalf of the database instances. If you want to control how many CPU resources a specific database instance can utilize, you need to utilize features like instance caging, Oracle Database Resource Manager. So it's Oracle-specific features to restrict how many resources the database instance can use. There's no specific ARX mechanism to say, okay, that database instance and all the processes can get only CPU. There is a feature, but I have not seen it much used. Let's put it this way.
Okay. Well, thanks. So we are out of time. So I know there are some questions in here we didn't get to, and like I said, I'll capture the questions log, and we'll see if we can't get some questions in there and post it on the wiki along with the presentation materials. So with that, next week, everyone, Ralph continues this, talking about, as this chart here says, I/O, networking, and other miscellaneous things that he's going to cover. So be sure to join again a week from today, and we'll wrap this up then. With that, I hope everybody has a good week, and thanks, Ralph. Looking forward to part 2 next week.
Okay, thank you, Joe, and everybody, thank you for attending. I hope it was helpful, and if there are specific questions, my email ID is, I think, at the top of the presentation on the first page, so you can definitely reach out to me and ask specific questions.
All right.
Thank you.
Yeah. Thanks.
Bye.
Bye.